3, 2, 1, 2.3. Let's get going. Alright, so we have learned how to solve our first class of first-order differential equation, the separable ones. So now let's go for the big dogs, the linear first-order differential equations. Alright, so recall that any first-order linear differential equation will look like this, right? Suspiciously looks like a polynomial. So we have a constant term with some huge quotes around that, right? A function involving the independent variable, which in this case is x, a coefficient on y, and then a coefficient on the derivative. And so these are all functions a, b, and c. So, for example, this right here is a first-order linear differential equation. In this case, my function, I'm using the variable c to represent that, and x as my independent variable. So note that this equation is not separable. Okay? Good luck separating x and z using multiplication. You just can't. They are being separated by addition. Okay. Well, like we talked about, linear equations are those where we have adding, scaling, and differentiation with respect to the independent variable. So the separable ones, we took care of the multiplicative case, so now we're going to attack the additive case, the linear equations. Okay. So how are we going to go about solving it? Okay. Well, let's see. What should we do? Well, let's play around with this formula up here first. We'll revisit this one and solve it in a moment. But let's play around with this. Okay, so we can always write it in its standard form by dividing out by the leading function a of x. Something that you do with polynomials, right? Divide out by its leading coefficient, so it's got just a leading coefficient of 1. Those polynomials are always nicer to deal with, so a reasonable thing to do. Now what do? Well, we did this. Let me start at the left-hand side for a moment. Because you might not notice it, but your brain does. You've seen something like that before. The product rule says that if you take the derivative of a product, remember products were in our mind from separable equations, then I'm going to get derivative of the first times the second plus derivative of the second times the first. So the left-hand side almost looks like it's the aftermath of a product rule. Okay, right? And now, immediately, you should be thinking, oh, exactly, right? We spent all of that time in calculus learning derivative rules, so if we want to solve differential equations, right, if I know what the aftermath of differentiation looks like, I can work it backwards to solve a differential equation. Nice. All that stuff we learned actually mattered. There we go. Okay. So we want to turn the left-hand side then into something that looks like the aftermath of a product rule. It's almost there, right? It doesn't quite line up though. So what are we going to have to do? Okay. So let's multiply the standard form y prime plus p of xy equaling q of x by some function mu. Now, I'm being lazy notationally here. Mu here is a function of x. I'm not including that for reasons that'll become clear in a moment. But it is a function of x that multiply both sides by. Now, again, what do we want to do here? We want the left-hand side to look like the aftermath of a product rule. So my y prime matches my f prime. My y matches my f of x. So what do I want my mu to satisfy then? Well, mu is going to be my g of x in this case, which means that mu prime needs to coincide with mu times p of x. So in other words, we've got mu prime is equal to mu times p of x. And oh boy, that is a separable differential equation right there. Good thing I know how to solve those. Hoo. So this one's really slick, right? Because separating the variables is very nice. We'll have 1 over mu d mu. That's going to be the integral of p of x dx. Well, the integral of 1 over mu, we know what that is. It's going to be log of mu. Again, ignoring the absolute values. So solving then for mu gives me this expression. So mu then is equal to e to whatever p of x integrates out to. Okay. So with all of this said and done now, remember, what am I trying to do right now? I'm trying to figure out how to solve first-order linear differential equations. I've recognized that in its standard form, the left-hand side almost looks like a product rule, and I've now figured out the thing I need to multiply it by to turn the left-hand side into a product rule. Right? And the reason for doing that is then the left-hand side is just one derivative, which means I can then integrate both sides. So, if I return to this expression right here, letting mu be e to the integral of p of x dx, we just verified that this is the choice that turns u p of x into u prime. That means that the left-hand side is a derivative, so integrating gives me an explicit solution for y. Right, so my differential equation now is turned into this. Solve this integral, divide by mu. I have now solved for y, and the differential equation has been defeated. Boom. So we take our differential equation, we multiply it by this value mu, it turns into this integral, and then we're done. Nice. So because mu gets multiplied in, so it becomes a factor that allows us to integrate, we then call it an integrating factor. There we go. Right? Words mean things. Right? There we go. Okay, so now that we've got the method for solving linear differential equations, let's see it in action. Okay, so let's go back to z prime plus z equals x squared plus 1. So the first thing we note, it's a linear equation. The next thing we want to go, is it in standard form? Is the coefficient on z prime just the constant function 1? Indeed it is. So, my integrating factor, right, I can now figure it out. Specifically, it's going to be the integral of p of x, in this case is 1. Integrate that, we get x. Now note, I am not including a plus c here when I did this integral. Constant abuse, right? And there's a good reason the plus c isn't up here. Note that the differential equation will turn into this because we've guaranteed that multiplying this by mu will turn it into this, so we can just go ahead and jump to that step. Note that if I had my plus c here, well, it'd be on both sides of the equation, and they would just cancel each other out, so who cares? So we don't even include it to begin with. Okay. All right, so our differential equation must become this expression, thanks to the integrating factor. So we integrate the right-hand side, and again, this would be an integration by parts, so, fill in the details if you like. So we know the right-hand side is equal to that. We have the left-hand side is e to the x times z, divide the e to the x out, and boom! We've got our explicit solution to the differential equation. Nice. So here we see linear equations really being very nice, right? And as we go forward in this course, we're really going to see linear things are very good, right? We like them because they can be solved. And as we just saw here, they can be really solved. They can be explicitly solved pretty easily. Just identify an integrating factor. We know that multiplying it will turn the left-hand side into a product rule. So when we integrate, we are going to arrive here. And just boom, boom, boom. Just take care of the thing there. Not too bad. So linear equations, they're beautiful. They're wonderful. They work out great. Okay. All right. Now, that was a lot of fun. But before we jump over to another problem, let's take a moment to further reflect on what we got here. Okay. Right. Now, in the real world, when you're faced with a mathematical problem and you work out the solution, right, getting the answer is great. But we don't want to just stop there. We want to unpack that answer. Okay. So we've just verified, using an integrating factor, that the general solution, the z prime plus z, is equal to x squared plus 1. So in other words, what's the function with the property that its derivative plus itself gives me x squared plus 1? Here's the function that does that. X squared minus 2x plus 3, which that on its own is not too surprising if we think about what's going on. I need a function's derivative plus itself to give me a polynomial. Obviously, a polynomial would probably work, so that's not too surprising. This C to the negative x term might be the weird one where you're like, why did that decide to show up to the party? Well, note that it would eliminate itself when you take the derivative, but anyway. So we've got this nice general solution. See, look what I'm already doing. I'm unpacking that answer, right? Not only do I know this answer works by knowing a factor, the answer also makes a lot of sense based on what the derivative, the differential equation, is telling me is true, right? I read the equation, looked at the answer, and said, yeah, that lines up. All right, so, right, things you want to do when you've solved something, right? It's not, you don't just get the answer and walk away. You look at it and go, all right, is this good? Is this really telling me anything? So not only does the answer line up quite nicely with what we got on the left-hand side, differential equations are used to model physical phenomena, right? Physical reality, we describe it using differential equations. So that general solution right there is giving me a formula describing how the physical phenomena would behave, right? Whatever this differential equation might have been modeling, this is giving me the function telling me how it should work. So one of the things we want to do whenever we get a solution to a differential equation is think about long-term behavior, especially if it's modeling a real-world phenomena. We want to know, well, as time goes on, what happens? Okay, so note that if we let x get really big, c e to the negative x is going to get small. It's going to get really small really fast. Right, and even if c is a gigantic number, even if c is Graham's number, right, one of the biggest numbers seriously used in mathematics, right, or if it's tree of 3 or something, there's some obscenely large numbers that are out there. What's the big one? Busy Beaver 768, if I remember right. That's the number that's just like unfathomably large. Right, so there's some huge numbers out there, but e to the x don't care. When x gets big enough here, that's e to a negative, that's 1 over e to a humongous number. E to a power gets huge, laughably fast. This is going to go to 0 eventually. So that means, for big enough values of x, my function z, this plus c term here really doesn't matter. At some point, this is just a grain of sand being added to the beach. Okay, so in this case, what we would say is that x squared minus 2x plus 3 is the steady state solution of the differential equation. Meaning that as time goes on, as you look at the long-term behavior of the function, this is really how it's going to behave. So if this was modeling some physical phenomena, we would basically go, it's essentially this polynomial plus some error term, essentially. There's some noise showing up here. Okay, right. So this kind of analysis that I just did, right, and I was doing a lot, right? I was unpacking a lot of the information that was given to me here. This is something that is essential to differential equations, right? It's not enough to just solve it and be, okay, I'm done, I solved it. We want to look at the answer, because the answer here is supposed to be telling me something about how physical reality works. So we want to start, right, investigating it. Right. So this sort of thing is the kind of thing we're going to do with differential equations, and maybe something on, I don't know, a problem list I'm going to give you beats me. All right. Okay. Anyway, it's time for another one. So, again, you should be watching this with pen and paper next to you, taking notes. Math is not a spectator sport. You learn it by doing it. So this would be a great time to pause the video and solve this wonderful initial value problem I've got right here for you. So go ahead and do that. All right, now if you're rejoining us, let's go ahead and solve it. Okay, so we look at this, we identify it, right? We see it's first order. Okay, now we know how to solve separable and we know how to solve linear. So if you look at this, we see, okay, I'm not going to be able to separate this, right? And separable means we're separating multiplicatively. That plus sign right there is saying you can't do that. So this is, in fact, linear. All right, and we check that, of course, because this is landing in the form, so we know it's linear, right? The only things affecting my dependent variable, my unknown function, are scaling, adding, and differentiation with respect to the independent variable x. So the first thing I want to do is clean it up, right? I need it in standard form, so I'll divide out by x, and that will give me this. Okay, so now I identify my integrating factor. It's going to be e to the integral of the coefficient function on y, in this case 1 over x, which integrates the log, which, hey, that's real convenient, gives me x. All right, so now we got that. So the differential equation then will become x times y, which will equal the integral of the right-hand side of the standard form, not this, the standard form, multiplied by x. Well, hey, look at that. We got x in the top, x in the bottom, they cancel. Integral of e to the x, well, the derivative of e to the x is itself, so it's integrals itself. Now our plus c shows up to the party. Boom, we've now got an implicit equation. Alright, so now what do? Well, we've got some initial conditions, so let's solve for y. And as I recommended, if you can make it explicit, always do that first before you solve for the initial conditions. Okay, so let's solve. Divide out by x, plugging in the initial condition now gives me 2 is equal to y of 1, plug in 1 for x. I get e plus c, solving for c gives me 2 minus e. And thus we get our unique solution to our initial value problem. E to the x over x plus 2 minus e all over x. Now note the way that I wrote it like this because if you were to let x get really large, right, if we're going to find the steady state term, this term right here is going to go to 0. The top is a constant, the bottom is x. If x gets big enough, this gets small. So in the long-term behavior, the solution is really going to be e to the x over x. So this will get small very quickly, right? Even if you go to x is equal to 100, this has already gotten quite small. So anyway. Now, as we just talked about, it's not enough to just solve it if EQ and wipe your hands and walk away. We want to do some analysis. We want to look at the solution, unpack the answer, think about it. Now, something that we want to address, especially with this one, is domain. Because I was making some moves in the previous slide that you should have been feeling a little skeevy about. Especially this one right here when I made that cancellation. Even though it's fine, and even when I did the division, it's fine, there should have been that moment where somewhere in your brain you're like, wait a minute, what happens if x is 0? Right? Because I never said anything about where x is coming from. So let's talk domain. So we've just verified that the unique solution is indeed this. And remember, our uniqueness and existence theorem had something going on with it. What would the domain be as a solution? So we've already discovered that in order for me to have actually done this, I needed to have implicitly assumed that x was not 0. Right? In fact, when x is equal to 0, the derivative would be killed. And that's an example of something called a singular point, which that's some deep lore differential equations. Won't get into that, but if you're interested, pursue mathematics a little bit further. Anyway, so this we know is a unique solution to the initial value problem. But if we're talking domain, we got to be very careful now. Our theorem told me that the unique solutions to initial value problems, the domain is an interval. The domain of my function y here is any real number except for 0. But that's not an interval, right? It's a union of two intervals. Right here, I'm hopefully, right, if you've ever seen the union notation, don't get too crazy about it. I'm just saying this is representing all real numbers other than 0. The domain of my function doesn't include 0, but it's not an interval, so the theorem telling us what solutions to an initial value problem should look like is telling me that even though this function is defined on a much larger set as a differential equation solution, I need to make a decision as to what interval it's defined on, right? The domain of a solution to a differential equation needs to be an interval. right? Otherwise, the uniqueness part starts getting wonky and the existence gets wonky as well. So the initial condition, right, when I write y of 1 is equal to 2, what I really mean is that the solution has to pass through the point 1, 2 in the xy plane. So x is equal to 1. That means that my domain needs to allow for x of 1 to be a value, which means that the domain as a solution is all the strictly positive real numbers, right? Avoiding the singular point of x equals 0. Okay. So this is something that you also need to keep in mind once you've solved the differential equation, right? What's the admissible values of x? And you're actually going to discover, for some of the solutions that you'll get, you've really got to be careful, because the domain might not go off to infinity. The domain actually might be like an interval from 0 to 5 or something like that. So that tells you that there's some, I gotta be real careful about when I set up these solutions, right, and what inputs are allowed and which inputs aren't, right? So that's very important when you're modeling something. What are the admissible inputs for what's going on, right? If it's time, usually you don't allow time to be negative. If it's a length, you don't like negative lengths, right? And other sorts of things like that. So here we see some qualitative analysis being done here, right? Right, we did the analytical, the qualitative, the quantitative analysis, right? We got a solution quantitatively, but now we're addressing qualitative issues. So, yeah, I know, you don't like the sound of that, but something you got to do, something to keep in mind. All right, so yeah, we in general aren't going to harp too much on this sort of stuff, but these are things we do want to address and things we do want to think about while we go further and solve our differential equations. Okay, so we've conquered separable differential equations. We've conquered linear ones. There's another type that we're going to conquer, and we'll find out next time. All right, see you then.